This video and the next one will be devoted to the prediction part in the Kalman filter. I got these equations from Wikipedia, and during the next two videos we will explain every letter of them. In this video we will focus on this part and this part. So let's review what we already know. When we have a Gaussian variable in one dimension, we know that it is described by two parameters: the average mu and the variance, which is sigma squared. What happens when we extend it to multiple dimensions? We are left with the same thing but in a matrix notation. Not so scary. The mean turns into a vector mu, which is the vector of a lot of means, and the sigma squared becomes a big sigma, which is the variance covariance matrix. The mu vector consists of mu1, mu2, mu3, mu4, and so on. What will the sigma matrix look like? We know the diagonal elements contain sigma 1 squared, sigma 2 squared, sigma 3 squared, etc. And the other elements contain the covariance element, meaning sigma 1, 2, sigma 2, 1. We can say two things about the sigma matrix. First, it is a square matrix, and second, it is symmetric, meaning sigma ij equals sigma ji. So far, everything looks familiar. How do these things work in the world of Kalman? When we talk about Kalman filter, we have different names. The mu vector is called the state vector, x. The mu vector is called the state vector, x. The state vector will contain all of the parameters that we want to track. For example, we can say that x at point k equals position and velocity. Here we have a Kalman filter whose state vector contains two parameters, position and velocity. In the same sense, it could have also contained four parameters: x position, y position, x velocity, y velocity. This is called the state vector. What will happen with the sigma matrix? The sigma matrix will become the P matrix, which is exactly like the sigma matrix, but we will call it matrix P, or the uncertainty matrix. It will tell us just how much our estimation or approximation as expressed in the state vector is accurate or not. So let's recap. The state vector x describes the best guess for the position as well as the velocity, and the P matrix describes the uncertainty in the state vector. One of the beautiful things about the covariance matrix is that you can get insight of one parameter from the other. In order for the last sentence to be clear, let's think of a simple example: 1D motion with constant velocity. Assume that at times t equals k, my robot was at a certain point. Let's call it xk. And remember, we have a constant velocity model. Now, if I know that from the last measurement delta t has passed, what I know is that the new position of the robot should be over here. Now, what x at k plus delta t equals? If I know that the velocity equals v, I can write the following equation. X at k plus delta t equals x at time k plus delta t times v. On the other hand, if I want to express the velocity at time k plus delta t, I can write the following equation. V at k plus delta t equals what? V at time k, because we assume a constant velocity model. This is basically what I told you. I can get insight regarding the position from knowing something about the velocity. Why? Because there is a connection, a correlation between the position and the velocity. And this is extremely important when it comes to the Kalman filter. Now, Kalman filters are based on linear dynamical systems, or dynamical systems whose evaluation functions are linear. What do I mean by linear? Is that you can take the equations and write them in a matrix notation form. In our example, I can write position and velocity at time k plus delta t equals a matrix of 1 delta t 0 1 times position velocity at time k. This matrix is called the F matrix or the A matrix, but the most important name is the transition matrix because it allows us to take the state vector at point k and transfer it linearly, assuming our model is linear, to point k plus 1 or k plus delta t. Let's see a graphical representation of what I just showed you. This graph describes two dimensions of velocity and position. In essence, every point on the graph describes 2 points, one of velocity and the other position. For example, this is where I am at x of k minus 1, the previous state. I am only in one spot, right? I have a specific velocity and a specific position. This is v at k minus 1 and this is p at k minus 1. If that is the case, why do I have a circle? Because this circle describes the uncertainty. I have a certain point at which my mean is located, my state vector, but I still don't know. I have uncertainty. And I have a certain cloud of points where I say, I think that I might be here. The idea of the prediction phase is to take every point from the present state, including all the uncertainties, and transfer it to the next state, from xk minus 1 to xk. Every point, this point, the mean, will transfer over here. But there is another point which describes uncertainty. I don't know whether I'm here or not. Nevertheless, this point will transfer over here. And over here you can see the diagonal that represents the covariance, the correlation between the position and the velocity. This transition is the prediction phase of the Kalman filter, and it is based on what is called the motion model of the system. If your model is nonlinear, if you cannot write in form of a matrix, you cannot use the Kalman filter. But if the motion model is linear, then I can say the following. Watch. X at point k equals f, which is the transition matrix, times x at point k minus 1. And of course, x at k plus 1 equals f times x at point k. Again, the F matrix transfers the current state to the next state based on the dynamics of the system. But what happens with P? How do I transfer the P uncertainty matrix from the current state to the next state? In order to answer this question, we will use a rule from linear algebra. Assume that I have a vector x and its covariance matrix is sigma. What happens if I take the vector x and multiply it by a matrix A? Or what is the covariance of A times x? And the answer is that it will be A times sigma times A transpose. This is how the rule works. And this is exactly what we have here. P at times k equals f times p at k minus 1 times f transpose. At this moment, we have the two most important equations in the prediction stage, meaning we know how to approximate the next state vector or the next state best guess, and also, not less importantly, we know how to approximate the new uncertainty. Two things we didn't do, which we'll do in the next video. The first is to pay attention to changes not related to the state vector but affect the system, for example, acceleration. The next thing is to pay attention to noise, which is always there. Every system has noise, but here we ignored it. In the next video, we will introduce those two things and we will have the complete prediction equations.